I indicated earlier that the solid part of soil is composed of minerals and organic matter. The typical mineral particles are described as gravel, sand, silt, and clay. Let's focus on these mineral particles first and consider the question of what are the actual materials that give rise to these mineral particles. The original source of the mineral material, that is the greater part of most soils, is rock of one kind or another. There are three main types of rock, and these are: 1. Igneous rock, which is formed by crystallization of the Earth's core material, such as granite, basalt, and lava. One source of igneous rocks is volcanic activity and the process of solidification of cooled magma or molten rock. Now, in Ohio, we have no exposed igneous rocks, as the source of these rocks, the Precambrian period, is overlaid with thousands of feet of sediment. Orton Hall, shown here on the Columbus campus, is an excellent place where to learn about the geology of Ohio, and it's definitely worth a visit. Now, the second kind of rock is sedimentary rock, which includes limestone, sandstone, and shale. Sedimentary rock is formed by deposition and consolidation of mineral and organic material, as well as by precipitation of minerals from solution. The process that forms sedimentary rock occurs at the surface of the earth and within bodies of water. Sedimentary rocks can be seen in many areas around Ohio, as sedimentary rocks are the primary rock type found on the surface of the state. For example, the caves and rock formations that have drawn gawking tourists to the Hocking Hills of southeastern Ohio for at least 175 years are carved from the Black Hand sandstone, a gray to buff colored sedimentary rock formation that's up to 300 feet thick in places, and was laid down more than 300 million years ago when southeastern Ohio was at the edge of a shallow sea. Alright, the third type of rock found in soil parental material is metamorphic rock, which include schist, marble, and gneiss. Metamorphic rock is the result of the transformation of an existing rock type, either igneous or sedimentary, that is subjected to heat and pressure, causing profound physical and or chemical change. The spectacular geologic strata shown here at the Sidling Hill Highway Cut in Maryland shows the type of environment where metamorphic rocks may develop. The different types of rock that make up soil can influence different properties of the soil, with potentially important consequences for the types of plants that can be grown in an area. Let's consider one of the properties influenced by rock type that is central in plant nutrition, the pH of the soil. We will discuss soil pH in much more detail in another unit. Within the igneous, sedimentary, and metamorphic groups of rocks are some with a high silica content that tend to form acidic soils, those with a pH lower than 7, and others with a high lime content that tend to form basic or alkaline soils that have a pH greater than 7. Consider one of these rocks, for example marble, a metamorphic rock resulting from the metamorphism of limestone, composed mostly of calcite. It's a crystalline form of calcium carbonate. Marble is familiar to many because of its extensive use in sculpture and in construction. Marble and the limestone from which it is derived have a high pH. Soil that is derived from these parent materials likewise have a high pH. Much of Ohio, especially the northwestern half, lies on top of limestone deposits. Marble Cliff, a suburb of Columbus, is named for the marble and limestone quarries in the area. Would it come as a surprise that Columbus and the surrounding areas have soils with high pH? Probably not. Many plants, such as rhododendrons and azaleas, and other plants in the family Ericaceae, do not grow well in high pH soils. Although people have tried to for a long time, good rhododendrons and azaleas are difficult to grow in Marble Cliff. So a general advice for the residents of this community would be, stop growing azaleas there. Thus, you can see that understanding the origin of the parental material for soil formation is relevant to understanding the performance of certain plants in the landscape. The different types of rocks that are the source of parent material for soil are broken down by physical and chemical action of climatic factors such as water, temperature, and wind. Physical weathering, also known as mechanical weathering, is the breakdown of large pieces of earth material into smaller ones. Think of physical weathering as the disintegration of rock without changing its chemical composition. Water is important in the weathering of rock, either by its sheer force in breaking up larger pieces, or as we saw for the origin of sedimentary rocks, by materials settling out of water that can become a parent material for soil formation. Smaller pieces of rock or silt may be transported various distances and laid out in the bed of a lake, a beach deposit, or alluvial deposits of streams. Water trapped in rock crevices provides another means of physical breakup when fluctuating temperatures lead to freezing and thawing of water in the rocks. When water freezes in rock crevices, it expands, creating stress in the crevice. As the stress increases, the crevice widens, ultimately breaking the rock, which hastens the process of erosion. Glaciers have also been important in the weathering of rock. Glaciers covered large part of the North Temperate Zone in the recent past, about 10,000 years ago or so. The mechanical action of glaciers causes rocks embedded in the ice to scrape against other rocks as the glacier moves. Glacial action ground up and transported huge amounts of rock. This glacial till was compressed under the weight of the ice, and the soils that form from this parent material tend to remain dense. Ohio soils in the northwest half of the state tend to be heavier and, as noted earlier, more alkaline than in the rest of the state, in part because of the glaciation that occurred there. Spectacular examples of the power of glaciers can be seen in glacial grooves at Kelly's Island on Lake Erie. Because of the density of the parent material, soils originated from glaciated areas tend to be rich in clay that can sometimes be difficult to form. For example, clay soils crack open when dry, then the cracks swell shut when wet. Clay soils are characterized by their stickiness and ability to form ribbons when squeezed, so one can see that the physical weathering by water and glaciers gives rise to one of the most common soil types in Ohio. This physical weathering of rock to produce smaller particles that end up making up soil is greatly influenced by topography, or the surface features of an area. Relief, or the shape of the land surface, determines whether soil particles stay in place or where they end up, and how much water is held in the soil. Flat topography would have much less soil movement due to gravity and water flow than hilly terrain, where gravitational forces would cause particles of water to flow quickly downhill. However, wind tends to move soil more on flat than textured surfaces. Wind-blown soil particles are called less, spelled L-O-E-S-S. In some areas, they are the parent material of soils. These soils are lightweight and easily eroded by wind and water if stripped of vegetation. A common challenge associated with soils in flat areas is the potential for waterlogging. This is a common feature of soils in glaciated areas of Ohio, and such effects have consequences on the growth of plants. So clearly the topography of an area has a strong influence on soil formation and physical weathering. The weathering of parent material begins with physical breakup caused by wetting and drying, freezing and thawing, and abrasion as material is carried by wind and water. As particles become smaller, further weathering occurs through chemical changes in the soil minerals in the presence of water. Chemical weathering depends on water and temperature. The rate of chemical weathering increases by 2 to 3 times when the temperature increases by 10 degrees Celsius or 18 degrees Fahrenheit, for example. Now, an example of chemical weathering is shown by this interesting rock formation. The surface pattern on this pedestal rock is honeycomb weathering, seen here in the red circle, caused by salt crystallization. This example happens to be in Taiwan. Now, if we look in more detail at how chemical weathering itself occurs, you can see that the breakup of complex silicates typically found in rocks in the presence of acidic water results in the loss of potassium, which leaches out, forming an unstable intermediate that ultimately releases salicylic acid and simple salts, which are more or less soluble in water. The more soluble compounds are leached or washed down through the soil by water. Aluminum in complex silicates may be replaced by magnesium, forming clay minerals which can hold water and other ions in a kind of molecular sandwich. Other chemical changes depend on the availability of oxygen in the soil. Oxygen tends to be low in heavy waterlogged soils, and in its absence, soil organisms reduce metals such as iron and manganese to soluble forms that can be leached out of the soil. When soils are well aerated, these metals are themselves oxidized and insoluble. Iron oxide is responsible for the reddish-brown color of many soils. Soils low in oxygen tend to be black or gray. So weathering takes us from solid, impenetrable rock to a soft clay in which the mineral particles are swollen and permeated with water. This colloidal structure can shrink or swell depending on the availability of water. As it shrinks, cracks open up, and in some cases, plant root system can get torn apart. Now, minerals that leach down through the soil may precipitate out to form a hard pan at lower layers. In low rainfall areas, minerals can get drawn to the soil surface as water is pulled from the lower levels by evapotranspiration. Now this leads to salt accumulation, and such salt accumulation may eventually prevent crops from being grown in this area. This concludes part 2 of soil formation, where we have looked at physical and chemical weathering.